Greetings, dear audience. Welcome to another episode of Physical AI, powered by Phygital, where AI meets the real world. Yes, you heard correctly. AI meets the real world. Why? Because together with scientists and founders, we explore how machines and human behavior converges in space. And today, I have a very special treat for you guys. Mingming Gong, Professor Mingming Gong. Mingming, how are you?
Yeah, I'm good, Tommaso. Nice
What
to
a
see you
pleasure to
too.
have you and have a sync again about this so very intriguing topic where we can learn from each other and build a better future for us as human beings. Mingming, allow me to introduce you real quick to our audience. Professor Mingming is a professor of machine learning at the MBZUAI, which stands for Mohamed bin Zayed University of Artificial Intelligence, and he's leading research at the intersection of causal inference, generative modeling, and world simulation. So Mingming's work explores how AI systems can move beyond correlation, learning causal representation that actually captures how the world changes under action and intervention. He's a pioneer in causal representation learning, disentangled latent variables, and domain adoption. Mingming research connects generative modeling with structural world understanding, enabling agents to reason about cause, effect, and dynamics. And last but not least, his papers at Neuer IPS, CVPR, and ICLR have advanced how AI learns structure interpretable representation of physical reality and cornerstone for the next generation of embodied physical ground intelligence. What a pleasure to have you here, Mingming. Are you ready to take our audience into some very juicy questions about the topic of AI and the space called IRL?
Yeah, thanks for the introduction. It's my pleasure to be here. Yeah.
The pleasure is all ours. Well, let me kick off things here, Mingming, in preparation of this interview here, right? I saw that your recent works on OV Gaussian and open-ins Gaussian, meaning segment Gaussian points, right? So these segment Gaussian points into different, let's say, semantic classes, right? So why is this segmentation of Gaussian so important for physical AI, and what new capability does it actually unlock for agents operating in this complex real world environment?
Oh, yeah, that's a good question. Yeah, so right now many people are using Gaussian splat, this kind of representation, to represent the 3D world and also doing reconstruction from image or video inputs. Yeah, but we like from simply like reconstruction of the world does not really mean that we can understand the world, right? If we only have a Gaussian splash consists of lots of like Gaussian points. So that's just a representation of the geometry and the appearance. So you can like visualize the world, how it looks like. But with this kind of representation, we cannot really understand what the objects or semantics in the world. I think from my point of view is if our goal is finally to have some agent which can interact with the physical world, we need to first understand the world, not just represent it, but also understand. So in this way, I think it's a preliminary step which can allow us to separate the thing or decompose the thing into different objects. So if we can understand the thing from semantics and separate the thing into individual objects, that could serve us as some input for the further interactions between, let's say, human or agents with the environment. Yeah, so that's why we think the object level disentanglement is kind of crucial to bring the perception and the action. So as long as we have this kind of decomposed representation, then we can allow, on top of this, we can build a more advanced tools to do the interaction and the word modeling.
So the more the more machines truly understand nuances, not just look at things,
Yes,
the
yes.
better the probability of fulfilling in action in a safe and a proper manner, right? You mentioned semantics here, right? So did you already do some research on different semantic levels per objects, on how this results in certain actions, or at what level would you say semantics are enough for a machine to proper complete a job?
Yeah, I think there are different levels of semantic descriptions. So the first one is, for example, object class. Like in a room, you have chair, you have sofa, you have a lot of like other stuff. So this could be just described as an object class. And in the next level, if we want to go more fine-grained, right, description, you can have some more detailed like a text prompt as a reference or referring to different objects, like a car in maybe yellow color of some shape, or in a room you have some like cups with different shapes or different textures. So you can have this kind of more detailed or fine-grained description. And then the next level, I think, is more about not just a single description, but also modeling the relations or spatial relations of objects in a thing, like something object maybe next to me or on the left hand side or right hand side. So this kind of spatial position or spatial context is also one way to have this kind of understanding of the object interactions or relations in the world. Yeah, so this is kind of from different levels of description.
And then the relevancy of actual object affordances, right? How would you correlate that with the semantics?
Yeah, the semantics and affordance, they are kind of correlated from the, if we know some object, let's say a bottle with the like material glass, then we know we can roughly compute the right affordance for this kind of classes. So for other kind of objects, if they have different material, different texture, yeah, it has different affordance. Obviously, there's a correlation between these classes and affordance, but sometimes there must be some ambiguity, right? For some description, maybe you have different objects, but they may have the similar or same affordance. So this could not be just by looking at the visual appearance, you can see that. So then you need other kind of sensors to measure this measure this kind of data. So I think there's correlation there, but definitely it's not like a predictable 100 with 100% accuracy from just the semantics. Yeah.
So ultimately, we need still multiple intelligent points, right, that reveal the overall, or that bring the understanding to the machine, right, of the overall environment, so that you can learn the position, the texture, the semantics, right, the affordance of it, right, in order to complete then this very specific task. And in your research, what example with what specific job and tasks have you been playing around with?
Yeah, I think one application we working on is about robotic manipulation, like grasping objects for the robots. So in this case, we need to really understand for example, objects. If we ask a robot to grasp some objects for you, like a bottle of water, then we need to give the semantics, right? So robots could understand what kind of objects it needs to bring for you. And second thing is about, like you said, affordance, right? When the robot arm wants to grab something, then it also need to understand the affordance, what kind of pressure or force they need to enforce to grasp an object. So this kind of applications really need all these kind of physical properties to have a good prediction of the actions of robots.
Mingming, let's switch gears towards the understanding of the why, meaning the causality in physical AI, right? So you have been working on that quite a bit, right, and learning quite a bit, right, specifically in causal generative models, right? So causality is fundamental concept in science that is, for instance, obviously relevant to understand cause of diseases rather than just their symptoms, right? Why is causality causal representation crucial for physical AI system? What role does causality play in enable intelligent agents to reason and act IRL?
Yeah, okay. So this is kind of a question following the previous one. So in the question you just asked, that one is about for a thing, right? You just understand the objects, semantics in the thing, but only that one don't give us the clue how they would interact with each other. So for causal or causality, here really means that we have some rules of like physical rules, right? Which is uh, asymmetric, so not like a correlation. Correlation means that something they have some could happen coincidentally, but for causality, it's asymmetric relation. So basically, the idea is that if we want to achieve some goal, let's say change something, then we need to find this cause, and we can act on that cause, then we can change the effect. But on the reverse direction, we cannot change the effect, right? By change, we cannot get the cause by changing the effect, not in the reverse direction. So that's why we think the causality is very important. So only we understand the causality, understand these kind of asymmetric relations, we can do the right action to change the world and get the outcome we need. So this is more in a high level. I could also give some examples. For example, let's say just go back to the robot example. So if a robot they must learn that, for example, when they push a button, then they can open a door, right? So that is to say, without causal reasoning, then it may treat button pressing and the door opening as a coincidental patterns rather than the cause and effects. But for our human beings, we have lots of this kind of knowledge built in our mind. So we know that there's a relation, causal relation between push a button and open the door. And every time, if we want to open a door, we will push some button or like, so in this case, yeah, if we enable the agents, the robots to also have this kind of capability, then it will learn how to really interact with the world and also get the outcomes that the robots would like to do to achieve.
And how would you be training the understanding and categorization of causality?
Yes, now then, like multiple ways. The traditional way, we come up with we call the tabular data or numerical data. So, for example, we can collect the data between different entities. Like if you push a button, the door opens, right? Uh, this kind of correlational data. But from this correlational data, we need to add in prior knowledge. So for example, this could be built in the knowledge base, or nowadays it could be built in the language model. So the knowledge base is basically built by doing experiments by previous scientists. So scientists have done lots of experiments to figure out which one is the cause, which one is the effect. There are also some like in the real world, there are also physical equations we can follow to encode the cause and effect relations. So this is a common way where we don't just need the data, we also need other kind of prior information telling us a knowledge where which variables could be a cause and which could be effect. And yeah, another way is more like from a statistical point of view, sometimes if you have just observations, like we observe data every day, we can also infer the cause and effect relations, right, from the data. So under some technically under some mathematical conditions, we can also infer the cause and effect relations by just looking at the observational data. So let's say we observe lots of video data. From this video data, because there's some temporal relations in the data, so we have the knowledge that the past usually the cause right, of the future. So this kind of asymmetric relation could also allow us to discover the cause and effect relations from data.
So basically, you have a scene within a video, and you say in a specific point where the action is taking place, you say time -1, -2, and then you project basically of what the next action is, and you keep on training it, right?
Yes,
And
that's
how
one.
much, I mean, sticking to your example here, Mingmon, right, of clicking on a button, right? Obviously, if the button is correlated to a door, then that's the action, right? But then you need to train it on multiple possible outcomes depending of what the true cause and reactions are, right? So if the button lights a light, right, then it's different. So, and that is still related to the actual data that you are training the model with, right?
Yes. Let's say if either human or robot has seen lots of video data, and in almost all the videos, pushing the button happens before the door is open, right? Then we can safely draw the conclusion that the pushing the button is the cause of door opening. Then this causal relations could be learned from data. And next time the robot know that I need to push a button to open the door.
And going back to the topic of data, are you using and are you leverage for test purposes existing data, or do you have a venue and an engagement model where you're collecting specific verticalized data? Like, are you using things like YouTube, or are you building something that goes beyond that to train multiple actions and correlations?
Yeah, so currently we rely on the web data. So basically, like you said, the videos from YouTube. We download some videos in YouTube and do some data pre-processing to get the data we need to train this kind of model. So yeah, for academic use, I think this is a common practice.
And how much is enough data that you say you have solid results?
For us, I think if we, let's say, identify some simple rules like pushing button and open door, that doesn't need much data. So yeah, maybe like hundreds would be enough. But the world is so complex. There are lots of kind of relations, right? I would say like a foundation model would be essential if you want to build a very general model which can model all kinds of these kind of causal interactions. That would be a huge amount of data to train such a foundation model.
So are you indirectly saying that in order to master one specific cause and action, that one would focus on more of a small model rather than a large model in specific segments?
Yes, our current research, I mean, because we are in university, we don't have lots of resources to do very large scale problems. But I think the idea could scale up. If you have more data, you can learn not just the simple, right, a set of rules, but maybe more general, this kind of causal rules or physical laws in the world. If you have
Great.
lots of data, yeah.
Mingming, congratulations on your research, congratulations on your endeavors. Leave the audience with a future back vision of yours. So, what needs to happen, and what are maybe some of the core pitfalls that you see, the challenges, right, in order for the machines to truly have a fluid way of interpreting the real world? What can you share with us? What's your vision?
Yeah, so from my point of view, I think because most of the data we observe is correlation, right? Like in the example, when you push a button and open the door, this is also correlation. But sometimes we can use a time, this time to distinguish between cause and effect. But in many scenarios, there might be no temporal information, or the temporal information is not complete or not correct. In this case, the model could learn some we call the spurious correlation. So there might be no causal relation between two entities, but the model thinks there are, but there's no relation there. In that case, the like agents could learn a wrong relation. Then when they do action, maybe there's no response at all. So I think we need to make sure we are really can learn this kind of true causal relations from data, not the fake ones. Yeah.
And how do you avoid having the false positives or mitigate that? What's the plan there?
Yeah, I would say now there's no perfect plan to mitigate this issue, but we try to reduce such cases as much as possible. I think one way is to really make the mathematical assumptions very clear. So, for example, under what kind of condition we can really learn such true relations from data. And for each model, we need to make the assumption quite clear. And when we go to the real world, we need to check whether the real world scenarios fits into the assumption. Otherwise, theoretically, maybe it's not possible to learn the relations from data. Then you need more information. For example, you may need to include some experimental data where you do some experiments, not just observe the world. You need to really do some action, right, to change the world and to see the consequence.
So more leaning into guided and supervised learning then, right?
Yes, you really need to do this kind of interventions to see the outcome.
Awesome. Well, thank you so much, Mingming. I really enjoyed the chat. Again, congratulations on your work. I would like hereby to invite you to join us our Physical AI Symposium in Silicon Valley, which takes place on end of April. For those who want to know more, here is the link, right? And I'm pretty confident that regardless if you are in Silicon Valley or not, you can tune in also remotely, sign up. And yeah, Mingming, here to help. I'm very excited to work alongside you in this endeavor of create a world that is more intelligent and not only for machines, but also for human beings, for us to have a more pleasant way of living on top of this analog world, right? Thank you so much for your time, and I'll see you in the metaphysical dimension, and I see you in the phygital dimension, right? Thank you so much, Mingming. Bye.
Thank you. Looking forward to the exciting event.
Thank you so much. Bye.
Bye.